Good morning, everyone. Let me just see if the stream, okay, the stream is healthy. Okay, I can start. Good morning, everyone. My name is Lucian Pullen, and I will be your tutor for today. Okay, now, today we'll be covering some questions on electrical potential. Okay, I'm just going to talk a lot, just going to head straight into the problem now. Question number one is all, forgive me, it's very dusty in this studio, is already on the board there. Okay, yes, fine. Okay, now in today's session we'll be doing some questions, like I said, on electrical potential, okay, which is a very integral part of this semester's work. Okay, because without this you won't be able to understand circuits and the related concepts. Now, points question one says the following. Question one states the following. Okay, points A and B are each the same distance r from two unequal charges. Okay, so we have 2 points A and B. Okay, points A and B are the same distance from two unequal charges, plus q and plus 2q. Okay, so one of these charges is twice as large as the other one. Okay, now the work required to move a charge q from point A to point B is, now, first of all, we need to picture what is happening. Okay, first of all, they tell us that points A and B are each the same distance from two unequal charges. Points A and B. This is the first charge, charge number one. And a distance from this charge is point B. Let's say this is point B. And they say point A and B are each the same distance from two charges. Now, the only way that each of these charges is the same distance away from it is if it's a square. Okay, if it's a square, so points A and B are each, so point A is a distance, let's say this is a distance of r. Okay, so let's say that's a distance of r, and that's also a distance of r. So point A and B are each the same distance away from this charge, which is, in this case, let's call it point just positive q. Okay, this is positive q. Okay, and they are also, this is positive q, and point A and B are also the same distance from another charge, plus 2q. Now, this is the only way that each of these points are the same distance away from these two charges. Okay, so that's the setup. We have point A and B the same distance away from positive q and the same distance away from negative q. Each of them is that same distance away. Right? This is the only setup that works for that. Now, we have each of these distances r, so meaning this is a square. Okay, so the question is, what is the work required to move a charge q from point A to point B? Okay, so this is point A. So what's the work required to move a charge from this point to that point? Okay, now first we need to calculate what is the potential here and the potential there, so we can calculate the difference in potential. Now, the potential at this point A, the potential at point A, let's work it out. The potential at point A is equal to, remember, the potential due to point charge is equal to K Q 1 over R and so on, right? Point, let's call it I, for doesn't matter how much many you can add, plus so forth. Okay, now at point A there are two charges. Okay, there's a plus Q and a plus 2Q that has an effect on the potential at point A. Now, K times point Q plus Q over the distance R, and then of course 2Q plus K times 2Q over R. 2Q here also has an effect or adds to the potential at point A. Okay, so this charge has an effect on the potential, and this charge has an effect on the potential at point A. Now, these are two charges, okay, that have an effect on the potential at point A. So the potential at point A is equal to, let's add them up. If you add them up from your arithmetic from primary school, it should be 3Q, 3KQ over R. That is if you add up KQ over R plus 2KQ over R. You will get 3KQ over R. That's the potential at point A. Now, this is going to be exactly equal, since they are the same distances and they are the same charges. This is going to be exactly the potential at point B. Okay, that's going to be exactly the potential at point B. The potential at point A will be the same as the potential at point B because these charges are each the same distance from point A and point B. Okay, so now we can say that the change in the potential from A to B is equal to VA minus VB. VA minus VB, which is equal to 0. So the change in potential from A to B is 0. Okay, so the change in potential from A to B is 0. So the change in potential from A to B is equal to 0. Now, the work done, okay, work done in terms of potential is equal to the charge multiplied by the change in potential from A to B, which in this case we've already established is 0. So the work done is 0. Now let's check if 0 is an option. Let's move. See, there is 0 there. Let's check if it's correct. Yes, indeed, it is correct. So 0 is indeed the option there. The correct option, I should say. Now let's go on to question number 2. Let me see. Is the entire... Okay, there we go. Question number 2. Let me erase this. Question number 2. Several charges, in the neighborhood of point P. So several charges in the neighborhood of point P produce an electric potential of 6 kilovolt relative to 0 and an electric field of 36 in the I-hat direction at point P. So the net electric potential due to these charges is 6 kilovolt and an electric potential of 36 newtons per coulomb in the I-hat direction at point P. Now determine the work required of an external agent to move a 3 microcoulomb charge along the x-axis from infinity to point P without any net change in the kinetic energy of the particles. So, how do we go about this? Work is equal to charge times the change in the electric potential. Okay? Now, the charge is a 3 microcoulomb charge. 3 times 10 to the negative 6 coulombs multiplied by the change in potential relative to infinity is equal to 6 kilovolt, which is 6 times 10 to the 3 volts. Now, if we multiply that out, 3 times 6 is 18. That is negative 6 plus 3. That's negative 3. So 18 divided by 3 is 0.018. And that is in joules. So this is the answer. This is the amount of energy, the amount of work required to move the charge from infinity to point P. Let's see if there is an option. Also, we can write this as 18 millijoules. Let's see if there is an option there. Number B is 18 millijoules. Okay, and that, ladies and gentlemen, is how this problem was done. All you have to do is to calculate the work. The problem was determine the work. Okay, and we know that there is a formula for the work. This is for question 2, by the way. I forgot to write that down. This is question 2. The formula for the work is the charge multiplied by the change in the electric potential. And we have the charge. It is a 3 microcoulomb charge that is moved along the x-axis from infinity to point P without a net change in the kinetic energy. And of course, the change in the potential relative to 0 at infinity is 6 kilovolt or 6,000 volts. Question number 3. Let's go to question number 3. It would seem that we're going fast. Okay, now the electric potential at 2 points in space is 200 volts and 300 volts. So the electric potential at 2 points. So let's call this points P and Q. So let's call these points P and Q. That's point P and that's point Q. Now the electric potential at point P is 200 volts, 200 V, and the electric potential at point Q is 300 V. Which of the following statements is true for moving a point charge Q from point 1 to 2? So if we were to move a charge Q, let's say we were to move a charge Q from 1 to point 2, so from P to Q, which of those statements would be true? Okay. Which of those statements would be true? Okay, number 1, the work done by an external agent to move Q from point 1 to 2 is positive. Okay, the work done is not positive. Okay, the work done to move it that distance is not positive. The work is negative. Okay, the work is negative. Now we can't determine the work done because we don't know the direction of V. V does not have a direction. Okay, because it is a scalar. Now the work done by the electric force exerted on Q in moving it from point 1 to 2 is, now we know that work is equal to negative Q delta V, which in this case negative Q is the charge, which is Q, and the voltage, the difference in voltage from Q to V, it is 300 minus 200, which is 100 volts. So the change in potential. So that is the work. Only C then is correct. Only C. Let me check. So yes, indeed, only C is correct. Only C is correct. Question number 4. Points A at 2.3 meters and point B at 5.5 and 7 meters are in a region where the electric field is uniform. Okay? So let's try and draw what is happening. There is a uniform electric field, and at 2 and 3, so somewhere here is point A, and point B is at 5 and 7, so somewhere here. This is not to scale, and the electric field is given by 4I plus 3J. Okay, so the electric field is equal to 4I plus 3J at. What is the potential difference VB minus VA? So what is that potential difference? How would I calculate that potential difference? Now, first of all, I need the distance, okay? Or at least this delta AB. The distance or the vector going from there to there. That vector will be 5 minus 2 in the I hat direction, see in the I hat direction, there's a point here. This point, it is 2 and 3, point 2 and 3, and this point is 5 and 7. Okay? So I want this distance and that distance basically. So to get this distance in the I hat direction, we minus 5 minus 2, which is 3 in the I hat direction, plus, and the distance in the Z direction, or in the J hat direction, in the J hat direction will be 7 minus 3. So 7 minus 3 in the J hat direction. And that gives us an answer of 3 in the I hat direction plus 4 in the J hat direction. So there we have a vector describing our the path we need to take from A to B. Okay, now we know that the change in electric potential can be written as the negative of the electric field dotted with the distance, which in this case the electric field is 4I hat plus 3J hat dotted with the distance, which in this case, or the vector, distance vector is 3I hat plus 4J hat. Now, if you dot this, okay, 4 times 3 is 12. 3 times 4 is 12. That's going to positive, that's negative. So you will end up with negative of 12 plus 12, which is equal to the negative of 24 volts. So that is, sorry, I forgot when I wrote down the formula. Let me just rewrite it again. The change in the voltage from A to B is equal to the negative of the electric field dotted with delta V AB. Delta AB. Let me just call it delta AB. That's not to confuse. Delta AB, the distance from A to B. You can call it D as well. Now, that's negative 4I plus 3J. I'm just checking if I'm still correct. Yes. I plus 4J. That gives me negative 12 plus 12, negative 24. Negative 24 volts. Okay, so let's see if there's a 24 volts. First, depends on the path you take. I did it from A to B. The reverse from B to A would just be 24 volts, of course. I did my path from A to B. It's the exact same thing. I just wanted a numerical answer. In this case, if I were to do it from the back side, it would be B to A. It will just be a change in the direction, which is just a change in the sign, which is 24 volts. Okay, now, question number 5. A particle with a charge of 2 microcoulomb is moving in a region where only electric forces act on it. Okay, so it's moving in a region where only electric forces act on it. And it has a kinetic energy of 5 joules at point A. So let's say this is point A, and this charge has a kinetic energy of 5 joules at point A. Now, the particle subsequently passes through a point B. Let's call point B here. Point B. When it passes through point B, it now has an electric potential of 1.5 kV relative to point A. Okay? So its potential is now 1.5 kV relative to this point. So relative to point A. So basically the change in potential energy is now 1.5 kilovolt or 1500 volts. Now determine the kinetic energy of the particle as it moves through point B. So we want the kinetic energy at this point here. The kinetic energy at point A equal to 5 joules. The kinetic energy at point B, what is it? How can we calculate it? Okay, now the work done to get to point B, the work done to move from A to B for this particle is the charge of the particle, or let me rather write down the formula first, times by the change in the potential. Now, the charge of the particle in this case is 2 times 10 to the negative 3. It's 2 microcoulombs. And then the change in the potential is 1.5 times 10 to the 3. And this gives you the work done to move from A to B is equal to 2 times 1.5, which is 3. And negative 3 plus 3 is 0. So it's 3 joules. So the work done to move from A to B is 3 joules. So it will lose 3 joules. Okay. The total work should be equal to the kinetic energy at point A plus the work done to move from A to B. That should be your total energy. Oh no, rather it should be like this. The kinetic energy at point A, let me write it simpler. The kinetic energy at point A, that 5, is equal to the work done it takes to get to from A to B plus its kinetic energy at point B. Remember, it loses some energy to get to point B. Okay? Now, the work at point A, the kinetic energy at point A is equal to 5 joules. The work it does to get to point B is from A to B is 3 joules. So its kinetic energy at point B is equal to the kinetic energy at point B then is equal to 2 joules. If you subtract 3 from 5, you get 2 joules. It uses of that energy, it uses 3 joules in terms of work to get from A to B, which means it only has 2 joules, 3 joules, which means it only has 2 joules left for its kinetic energy. So its kinetic energy should be 2 joules. Let's check. And yes, the correct answer is 2 joules. Okay. Question number 6. Question number 6. A particle A with a mass of m and a charge q, and particle B with a mass m and charge 5q are released from rest. Okay, so these two particles are released from rest with the distance between them equal to 1 meter. So when they are released from rest, the distance between them is 1 meter. Now, if Q is equal to 12 microcoulombs, what is the kinetic energy of particle B at the instant when the particles are 3 meters apart? Okay, so particle A and particle B are dropped into an electric field. They are released from rest and the distance between them is 1 meters. Now, what is the kinetic energy of particle B when they are 3 meters apart? Because there are two positive charges that will repel each other. So what is the kinetic energy at point B, 3 meters apart? So what is, first of all, let's calculate the potential energy when they are just 1 meter apart. The potential energy when they are 1 meter apart. The potential energy when they are 1 meter apart is K Q1 times Q2 over the distance between them. That's how you get the potential energy between them. So that's 9 times 10 to the 9 multiplied by the two charges. Okay, the Q charge is 12 microcoulombs, and the other one is 5 times 5Q, so 5 times 12 microcoulombs, and 5 times 12 microcoulombs is 6 times 10 to the negative 5 coulombs, and the distance between them is 1 meter. Now the potential energy initially between them is 6.48 joules. Oh, sorry, 6.48 joules. Now what is the potential energy when they are 3 meters apart? Let's see. The same problem, the same 9 times 10. Let me rather just write it this way. Oh no, we use the same formula here. 9 times 10 to the 9, 6 times, okay, that's 12. It should be 12 times 10 to the negative 6, and then 6 times 10 to the negative 5. That's how we get the potential 3 meters apart, and that potential energy is then, this by the way is not 640, it's 6.48. The potential energy is now 2.16 joules. Okay, so its initial potential energy is 6.48, but after 3 meters apart, its potential energy is now 2.16 joules, which means this distant difference in potential energy, it has lost to kinetic energy in a closed system. So the potential energy when it's 1 meter apart is 6.48 joules. The potential energy when it's 3 meters apart now, after they've moved apart, the potential energy is now 2.16 joules, which means it has lost energy, potential energy. Now, we know that this change in the potential energy, this loss of potential energy, is a gain in kinetic energy. So that change in the potential energy is just equal to its kinetic energy, which in this case is 6.48 minus 6.48 joules minus 2.16 joules, and that is equal to 4.32 joules. So it has a change of kinetic energy of 4.3 joules. Okay, now this is the potential and the kinetic energy added for both of these particles. Okay, now since their masses are exactly the same, they will have the same, they have different charges but the masses are the same, so they will have the exact same charge on each one of them. So we need to divide this kinetic energy by 2, which is what each of these charges will have. Each of them will have, thus each of these charges will have half of that. We'll have 4.32 divided by 2 joules, which is equal to, I worked it out, which is equal to 2.16 joules, which is approximately 2.2 joules. That's how much energy each of these particles will have. Okay, about 2.2 joules after they are 3 meters apart. And let's see, there's 2.2 joules. Yes, that is correct. They have 2.2 joules when they are 3 meters apart. Now, problem number 7 is rather an interesting one. There are 2 ways of doing it. One is using calculus, and the second way is much easier, and I will do it using the second method. Okay, now a uniform electric field of magnitude 325 volts per meter. Remember, we can also denote electric field in volts per meter, and is directed in the negative y direction. So in the drawing, that's the electric field going down. Now the coordinates of point A are negative 0.2 and negative 0.3, and the coordinates of point B are 0.4 and 0.5. Now this part from A to B is then there. Now what is the electric potential difference VB minus VA using the dashed line part? So if we were to move in that direction, now VB minus VA is equal to that part, the integral path from A to B, with the electric field integrated over with respect to the distance, the electric field integrated with respect to the distance. Now, if we were to do that, okay, you would find, since this electric field is uniform, it's not changing, okay, we can take the electric field outside, meaning the electric field can be 3 to 5 outside, and then we just concentrate on the distances, okay, the difference in the distances, because then it's 0.5 minus 0.3. Remember, it's 0.5 there where point B is, minus 0.3. That's the first distance. And to that, you add the second distance, which is that's the first distance, the electric field multiplied by the distance, the electric field multiplied by the distance, plus for the second part, that's for this first part from point B to this dot here. So from B to the dot here, now it has to go down from that dot there to point A. Okay, so it's again the electric field negative 325 multiplied by the distance, which is negative 0.2, subtract negative 0.2. So we are subtracting it from itself, so that part will be 0 eventually. And what we get is, okay, I've made it too thick. So what we get then is 325. That negative multiplied in is 325 multiplied by whatever's the sum in the bracket, which is 0.5 minus 0.3, which is 0.8. And this time this side will be plus, multiply the negative in, it's 325 multiplied by that, which is 0. So the answer will be 325 times 0.8, which is 260 volts. 260 volts. Let's see if there's an option for 260 volts. If you calculate it, you will find that the answer is 260 volts. Remember, we're moving from B to A. It would be negative 260 if we were to move from A to B. Okay. Question number 8. I'm going at a reasonable pace because some of you have said that these videos are too long, we take too long, so I'm just doing the answers, okay, how to get to these answers now, and explaining how I got them and the method of reasoning. Number 8. Question number 8. Okay. A particle with a mass of 6.7 times 10 to the negative 27 kilos and a charge that looks like a proton with a charge of 3.2 times 10 to the negative 19 coulomb. That's an alpha particle. Moves along the positive x-axis with a speed of 4.8 times 10 to the 5 meters per second. It enters a region of uniform electric field parallel to its motion, and it comes to rest after moving 2 meters into the field. What's the magnitude of that electric field? Now, first let's calculate the kinetic energy of this electric field. A half mv squared. Now if we were to work out the kinetic energy, we'd have a half. Its mass is given as 6.7 times 10 to the negative 27. Its velocity is 4.8 times 10 to the 5. So its kinetic energy when it gets into the field is 7.72 times 10 to the negative 16 joules. So that's its kinetic energy. But we know, well, this is the change in its kinetic energy, but we know because it comes to rest after moving 2 meters, so that's the change in its kinetic energy. Now we know that the change in kinetic energy is exactly equal to the change in its potential energy, meaning what it loses in kinetic energy since it comes to a stop, it will gain in potential energy. Okay, so that is now the potential energy. That change in kinetic energy is equal to the potential energy. Now we know a formula for potential energy. Let me just write a formula for the potential energy is equal to Q times the electric field in the direction of movement times the distance that we move through, x final minus x initial. Now the charge is 3.2 times 10 to the 9 minus 19 coulomb. The electric field in the x direction at that point is what we want, Ex, and the distance it travels is 2 meters. And the change in the potential energy we worked out to be 7,72 times 10 to the negative 16 joules. Seven comma 7 2 times 10 to the negative 16 joules. That's the change in potential. Now if we were to solve for the electric field, we would find Ex, the electric field, is equal to 1,2 times 10 to the 3 newtons per coulomb. That's 1.2 kilonewtons per coulomb. 1.2 kilonewtons per coulomb. Let's check the answer. And yes, it is indeed correct. Okay. Question number 9. If A, this point here, A is 30 centimeters and the distance B is 20 centimeters, Q is 2 nanocoulomb and big Q, capital Q, is negative 3 nanocoulomb. In the figure, what is the potential difference VA minus VB? First of all, let's calculate the potential at point A. Okay, so the potential at point A is equal to the potential due to charge Q plus the potential due to charge capital Q. Now, let me just write the correct distances. The potential due to charge Q, which is a distance of A away, while the potential due to charge big Q, which is a distance of A plus B away. Now let's substitute in all the values. I'll sub in Q, which is 9 times 10 to the 9. The charge of Q is 2 nanocoulomb. The distance A is 30 centimeters, so 0.3 meters, plus same thing for the big charge, 9 times 10 to the 9, big Q, which has a charge of 3 nanocoulomb, negative 3 nanocoulomb. And it is a distance of A plus B, which is 20 plus 30, which is 50 centimeters or 0.5 meters away. And thus, if you were to work it out, is 6 volts. Okay, the potential difference, the potential at point A due to those two charges is 6 volts. Now we do the exact same thing for point B. We do the exact same thing for the potential at B. Okay, the potential at B will be due to the charge KQ, and it's a distance of A plus B away, plus K big Q, which is a distance of A away. Now, this is 9 times 10 to the 9. The charge Q is 2 nanocoulomb. and the distance A plus B is 0.5 meters plus K, which is 9 times 10 to the 9, multiplied by BQ, which is negative 3 times 10 to the negative 9 over a distance of 0.2, and that gives you an answer of negative 0.54, negative 54 volts. So now we have the two potentials, okay? The voltage at A due to the charges is 6 volts. The voltage at B due to the charges is negative 54 volts. Okay. Now VB minus VA is equal to, oh, it's VA minus VB, sorry, it's the other way around. VA minus VB is then equal to 6 volts minus 54 volts, which is equal to 60 volts. 60 volts. Let's check if 60 volts is the answer. Yes, 60 volt is indeed the correct answer. I'll just check here. Last question for today. I know it's quite a lot and I don't like doing all of these problems. Okay, so question number 10. This is a fun one. Okay. An electric field is created by a positive charge. Distribution of the electric field lines and the equipotential lines, meaning where the potentials are exactly the same. Okay. Now we know that electric potential is equal to K Q R away. So if the charge stays the same, then the potential is dependent on the distance. So the same distance away, the potential will be the same. And the further away it is, the smaller the potential. Okay, so the further outwards from their charge, the bigger, the smaller the potential. Okay, now, so those are electric field lines and equipotential lines. Okay, which statement of electric potential is true? Okay, so first of all, they want to say which one is bigger and bigger. They want us to determine potentials, which is bigger. So let's determine it for ourselves. Potential A, the potential at point A is equal to the potential at point D, because they are the smallest, because they are the closest to the charge, and they are on an equipotential line, so they are equal, and they are bigger than the potential on the next equipotential line, which is point B. So they are bigger than the potential at point B, and that one is bigger than the next set of potentials, which are on an equipotential line. So the potential at point E is equal to the potential at point C. So let's see if there is a statement stating this. VA is equal to D. Okay, here's one. VA is equal to VD, which is bigger than B, which is bigger than C, which is equal to VE. Let's check if it's correct. Yes, indeed, it is correct. So we have done all 10 problems on multiple versions of how to ask problems on electric potential, and I hope that when you watch this you understand and at least get something out of it. Okay, I will see you next time. Take care. Bye bye.